So, two types of reactions. What's the same, what's different? Substitution reaction, we substitute the leaving group X for Y. In an elimination reaction, we still have a leaving group, but we have the Y take a hydrogen and make a pi bond, but we still have the leaving group. We've seen this before, so substitution versus elimination. This idea about a leaving group, we just maybe didn't know it when we did acid-base chemistry. All right? We break that hydrogen iodine bond, and the leaving group in this case would be what? It would be I minus. All right, that's the leaving group. We want leaving groups to be really stable. Right? Large atoms can disperse the charge, that makes them more stable. Right? Iodine is big, can disperse that charge, versus fluorine. Right? Like all wound up fluorine. What are other ways we could do this? Another example of acid-base chemistry with a leaving group. So it's like kind of relating what we already know. Right? Again, take the H, break the OH bond. So a carboxylic acid reacting with this, so we make water, of course. And we make something that looks like this. What can this do that makes it stable? It can do resonance. Resonance is a way to stabilize things. You want leaving groups to be stable, right? When you want a reaction to go, you want the thing that's falling off to be stable, to make it go forward. So you want things to be large, so they can disperse the charge, or resonance would be another really good thing to do as well. Resonance always stabilizes things. What does Sn2 stand for? All right, let's just get the basics. What does Sn2 stand for? S stands for substitution. N stands for nucleophilic. 2 stands for 2. No, 2 stands for bimolecular. All right? This has to do with the rate. Right? When we say bimolecular, that means 2 species are involved in the rate. 2 species are involved in the rate. What does an Sn2 reaction look like? This is an Sn2 reaction. It's one step. You substitute, in this case, the iodine, or the chlorine for the iodine. We, of course, balance our charges, adding some lone pairs. But the point is, both the nucleophile, which was the I minus, and the alkyl halide, the thing that's bound to a halide, halides are fluorines, chlorines, bromines, and iodines. Right, that alkyl halide, both things were involved in the rate determining step. There's only one step. Right, so both things were involved. All right, so if I look, knowing this is a one-step reaction, both the alkyl halide and the nucleophile matter for the rate. If I double the amount of nucleophile, I would double the reaction rate. If I used half as much alkyl halide, I would half the reaction rate. It'd be half as much. It'd slow it down. Which way would this reaction lean towards? Starting materials or products? Starting materials in this case. I minus is larger and more stable than Cl minus. So it actually would lean this way, right? The stability of the leaving group. So what this is showing us is the carbon that the leaving group is attached to, in this case it's the bromine. The less sterically hindered that carbon, the more reactive it is. So sterics slow down the rate. To the point where something like this, which is a tertiary, we call this a tertiary, this is a secondary, a tertiary alkyl halide doesn't even work for an Sn2 reaction. The nucleophile can't get to this carbon. There's too much stuff in the way. There's too much stuff in the way. The nucleophile can't get there because it's sterics. You see less carbons, makes it easier, so this is faster. 1 to 2 to 3. These are all primary. Right? These are all primary. But less carbons, less atoms makes it easier to get to. So what does this tell us? This told us that we went from S to R. That means we had an inversion of stereochemistry, an inversion. That tells us something about the orientation of this reaction, that the nucleophile needs to react in such a way that it comes to, we call this the backside attack. It needs to come from a certain direction. The direction matters. The orientation matters. So what does that look like in a molecular orbital picture? So, inversion. So how does this look like in a molecular orbital picture? We know, because this goes from S to R, we know something about where sigma star is at. We know the orientation matters. The OH has to come from 180 degrees away to break this carbon-bromine bond. So the way to look at it with a molecular orbital is, you have a carbon-bromine bond. In the bond, bromine's more electronegative. So most of the electrons in the sigma bond will be around the bromine. The opposite is true for sigma star. Most of where electrons are not at is on the more electropositive atom, which would be carbon. And that sigma star is mostly over carbon, and it's 180 degrees away from the sigma bond. When the nucleophile reacts with the electrophilic carbon, it's going to react 180 degrees away from the carbon-bromine bond. As these electrons go here, right, as you put electrons in a sigma star, you break the sigma bond. Anytime you put electrons in an anti-bonding orbital, you break the corresponding bonding orbital. And because this is here, 180 degrees away, you get inversion. So if you see inversion, that tells you Sn2 probably, right? Orientation matters. So we've already talked a little bit about leaving groups. So what do we want for our leaving groups? We want our leaving groups to be stable, right? That'll help a reaction go. If the leaving group by itself is stable, that makes it go, right? That'll make the reaction go forward. So something, I don't like think of these like weak and strong terms. It just bothers me. Iodine's larger, so it can disperse that charge. That makes it more stable, right? Something that has resonance as a leaving group would be more stable because it has resonance. Something that has a negative charge, right? So let's say you could have this N minus versus O minus. Which one's a better leaving group, N minus or O minus? Which one's more stable with a negative charge? O minus is more stable with a negative charge because it's more electronegative, right? So when you think about leaving groups, you're always thinking about stability, right? Stability. So you want things that are more stable. So use those ideas about resonance, size, and electronegativity to find the most stable thing for a leaving group. So what about nucleophiles? So if you want a stable leaving group, you actually want a reactive nucleophile, right? So it'll be just the opposite, right? If you want a nucleophile to have a charge. What kind of charge? Can nucleophiles ever have a positive charge? No, negative charge. So a nucleophile that has O minus versus just a lone pair, which one's more reactive? Well, the O minus is going to be more reactive, right? The charge matter. What's a more reactive nucleophile? O minus or N minus? Which one's more reactive? N minus, right? Nitrogen's less electronegative. That makes it more reactive. It's less happy with the negative charge. What about as you go down the periodic table, right? Things get larger. If you're larger, do you hold your electrons as tight? No. So an I minus versus a little tiny F, which one's a better nucleophile? I minus is. Because it doesn't hold its electrons as tight. It's huge, right? It has these electrons way out here, right? So things with negative charges will be a more reactive nucleophile, right? Charges first. If something has a negative charge, that's the nucleophile. Then you look at the periodic table. Across the row, if something has a negative charge, you want it to be less electronegative. That makes it more reactive for a nucleophile. N- is more reactive than O-. Right? Also, check out this. The size, the things on the nucleophile matter too. The sterics can matter for the nucleophile as well. Right? You don't want your nucleophile to be very big either. You want your kind of skinny nucleophiles, smaller nucleophiles. Less stuff on the nucleophile too. As you go down the row, as you go down the column, larger atoms are more nucleophilic because their electrons are farther away from the nucleus. Right? They're more willing to react. Charges, rows, periods. Solvent. For all these reactions, you're going to want a polar solvent, right? We talked about hydrogen bonding and all those intermolecular forces. It's going to kind of help us out now. So we want a polar solvent. That means we want it to have polar bonds. Now the question is, do we want it to be protic or aprotic? So protic means it can do hydrogen bonding with itself. Those are those OH, NH, SH, and pH. That's protic. Aprotic doesn't have those things. For an Sn2 reaction, we want it to be aprotic. Why? Because we don't want our nucleophile interacting with the solvent. What do we want our nucleophile to do? We want our nucleophile to react with the electrophile, the alkyl halide. If there's OHs, SHs, NHs, and pHs, our nucleophile could react with that. We don't want it to react with that. Right? We want our nucleophile to react with our alkyl halide, our electrophile, not the solvent. So we want a polar solvent, and we don't want any OHs or SHs or NHs or pHs. We want aprotic. So we want a polar solvent, so something like diethyl ether, right? Has polar bonds, but doesn't have any OHs, NHs, SHs, or pHs. Right? So something like this. So it can't hydrogen bond. Protic solvents can do hydrogen bonding with themselves. We don't want those because we don't want the nucleophile interacting or reacting with the solvent. Polar, aprotic for Sn2.